Hi folks, this is your professor Kent Schwitkus, and this time we're going to be talking about the Earth and Moon. Basically, as you can see by the front page here, I have some particular ideas about this particular chapter. We're going to be talking about such things as climate change, as well as what is the formation of the Earth. Now, last week we talked about how the solar system was formed. And part of that creation story is based upon information that we have gathered from the Earth. And so in that regard, it's important to understand just the information that we have from the Earth and how we have obtained it. In fact, personally, I think that's the most important part of it. Data is something that we can argue about, but we can also come to a consensus. Data, facts, and logic are things we can agree to. And that is the essence of the scientific method. We have to be able to observe these things together. This is not information, or this is not knowledge that is that comes from on high, that only one of us can obtain at any particular time, and that we can't share. These bits of information, these facts, are something we share together. Okay, so that is how we're going to proceed, and that is how science proceeds. Okay, so here is the interior of the Earth. It comes into three portions. We have the core, we have the mantle, and we have the crust. Now it turns out the core has two bits to it. It has a solid and a liquid portion of it, and we'll talk about that later. The mantle and the crust are basically rocky in nature. And when I speak about rocky, we're talking about things like you see at the beach. Now, you might know that if a lightning strike hits the beach turns, that portion that was hit turns into glass. Glass is silicon dioxide. The beach sand is typically silicon dioxide. Rocks that you see around you in the mountains or the dirt is silicon dioxide, more often than not. Now, naturally, there are other elements involved, but by far and away, most of it is just that, beach sand. So, it turns out also that the atmosphere is basically three parts as well, so we'll talk about that later. Okay, now the Earth's interior is mostly, is got these three bits to it. The inner core is solid, and is roughly the same temperature as the surface of the sun. Very interesting in that regard. It is about the size of Texas, as you can see here. So here is Texas, and we can't see the panhandle, but you can see where, the Texas coast on the Caribbean incorporates this region here, and then we have the other Louisiana, Alabama, Mississippi, and then Florida. But a substantial portion of it, you can see it's about the same size as the inner core. Now we also have a liquid core, and you can see it extends out a bit further, and then we have the mantle and the crust. The mantle is basically, you can sort of view it as sort of lava in consistency, if you will. The density of the core is 14 grams per cc, which is much more so than lead. Lead is about 10 grams per cc, and as it says here in the chart, the inner core is actually growing every year. Now the core grows because the liquid core is settling out on top of it, and it's cooling off. The whole Earth is cooling off, and for that reason the inner core does get larger. And now let me retreat one page here, and let me remind you that at high temperatures, which 6,000 degrees Kelvin is a high temperature, that would be roughly 12,000 degrees Fahrenheit, sort of roughly, going by a 2-to-1 factor of Celsius to Celsius to Fahrenheit. But normally you would think that something that hot would always be liquid. And as you can see here, it is the high pressure that is, pushing down on this inner core that is causing this thing to be solid. All right, now why the layers? Well, the layers have to do with an interesting process called differentiation. And I have a video that we'll see if it plays in a little bit. But basically, those things that have a higher density will sink, and those things that have a lighter density will float. So the metal core, or the core, is metallic in origin, iron and nickel mostly, but some things that are associated with that, which also are friendly with those materials, will also settle out there as well. Now, the inner core is basically, from what I can understand, is just a crystal, a single crystal of iron and nickel. You might say that I have to have two crystals there, but there's probably some mix-up between them. But basically, all the other stuff cannot be part of that crystalline structure. And so it gets expelled from the solid and sort of creates a more a layer here which is more contaminated with byproducts, with non-iron and non-nickel type materials, and so this type of stuff would diffuse back out. So this interior here has the highest density in the Earth, and then this out here, the mantle, has medium density, and then we have the crust, which is the lowest density, sort of is floating up on top. Okay, let's see if we can get this this thing to play, and look at that. It might just work. So wait a little bit, and here we come. Looks like I have to always go through so much stuff to get there. Now what we'll see here is just an experiment on the surface of the Earth. I mean, after all, some people are doing this. And what we'll see is a bunch of materials put together, and they are sort of separate in the very beginning, but you'll see that that as we liquefy the ice, then the washers will settle out to the bottom, and then the liquid water will be in the center, and plastics will be at the top. So this is sort of what we'd expect to happen with the Earth. In the very beginning, we had it was made of big mishmash of stuff, but then later on, as more material was added to the Earth, then we would have the metals floating or sinking down, and the light stuff rising to the surface. Oh, look at that. Okay, so the Earth's core has evolved, and it continues to change. And basically, we have, in the beginning, we had a molten core, was all entirely molten, and we had a mantle on the surface, and that was it. Now, between these places in the Earth's, as we go down in the depth of the Earth, we'll have these layers come about. The inner core basically occurs because the whole Earth is cooling off. After all, it is touching deep space, which is at 3 degrees Kelvin. And the interior is, the whole thing was molten at one time because of how much energy it takes for accretion to take place. So, not earthquakes, but comets and asteroids hitting the surface of the Earth, because they have lots of heat, as we saw with the simulation last week. So this whole thing, as it would cool off, then the interior portion, because of the pressure, because of the change in temperature, would freeze out. Now, it isn't frozen. When I mean freeze out, it's becoming a solid. So this inner core would be a solid, and it would steadily increase as the temperature escapes from the surface. Okay, so temperature is escaping out the surface, which allows for more transfer of heat from the interior portion to the exterior. All right, now at this interface right here, we have the inner core and the outer core. The outer core is liquid, the inner core is solid. as more material freezes out on this surface, then the impurities that are in the outer core are pushed out, right? Basically, crystals like the materials from which they're made out of, and they grow that way. So if you have a water crystal, water will freeze, and then more water liquid will crystallize upon the surface that we had just before, and that's how snowflakes grow. The same thing is occurring at the inner core. The inner surface here is a crystal, and then as more iron or nickel cools off, it will freeze attached to this interface, this pure crystal, and it will grow out, meaning that the impurities that were in the region surrounding this newly crystalline piece will then get pushed out. So right along here, we have a high density of impure metals in comparison to iron and nickel. Basically, we'd have chlorine, we'd have uranium, we'd have all these other elements besides nickel and iron. So part of what's going on is not only do we have heat being transferred out, going from the inner core to the surface of the Earth, but we also have a convection current caused because of the impurities. The impurities will want to diffuse out, and we have an additional current of motion caused by this change in density of impurities wanting to spread themselves out throughout the entire outer core. Now, what's happening in the mantle, my understanding, is just convective. Just the heat transfer from the outer core out to here, out to the crust, is just heat transfer, not diffusion. So this whole process of getting heat from the interior of the Earth to the exterior drives the creation of earthquakes and of mountains and the whole fault system. So here is a picture here of the tectonic plates of the Earth, major ones, Pacific Plate, North American Plate, and as you might get, this is the San Andreas Fault, and we live so close to it. So, I'll put in my plug here. Everybody should become, an expert at saving each other's lives. So take a CERT class, Citizens Early Emergency Response Team, or take first aid, CPR, all these things you can get, because it's just going to be us in the very beginning of such a disaster. And it's useful too. If you go with ski patrol, you can go skiing for free if you have the medical skills. Anyway, so much for my plug. Now, one of the examples here that I use is I typically go and have breakfast at a place called Fantastics. And what I like to get is the French toast special. And part of that is I get a little cup of maple syrup, and I normally eat my eggs first, and then have the French toast as a dessert, if you will. And by that time, there's a top layer on the maple syrup that is basically not liquid anymore. It's almost solid. And underneath it, though, is quite liquid. So that is sort of similar to what's going on with these tectonic plates and with the mantle underneath. So imagine these tectonic plates as being cooled off. There's sort of a layer, a scum layer on top of the mantle, and they move around on top of the mantle. Okay, so that's essentially what we have going on here. And earthquakes get created, or if you will, mountains and deep gorges, as you can see here for the San Andreas Fault, are caused because of what's going on at these interfaces between these tectonic plates. So the engine that drives this is the mantle underneath. Okay, so here is, we have this occurrence here cyclic behavior of the mantle underneath, and then on top of it we have this layer on top which has been cooled off, just like the scum on top of a little cup of maple syrup. So here is the mechanism, if you will, of plate tectonics. We have this molten rock which can move around, and where we have spreading occurring, we have this divergent boundary, and magma folds into here, and it's liquid, and you can see pictures on YouTube, I'm certain, of lava just pouring out of here. And and then this is an area of, if you will, C4 spreading. There is an area in the Salton Sea where we have a divergent boundary, and we have spreading going on there as well. So that's something you can visit. Now, at certain points we have places where the continents or the plates are actually coming together, and one subducts the other. Now, typically it's the ocean that is subducting underneath the other tectonic plate. But if you look over here in the Indian subcontinent, you have a subduction going on right here, which is causing the Himalayas to increase in size. So we have this region, the Indian subcontinent, is diving underneath the Eurasian plate, which is causing the Himalayas to increase in height. Here, for us, along in Los Angeles in California, we have a different type of plate, or a different type of fault system. We have a strike slip where we have motion in one direction, and then we have motion in the other direction. Okay, so we have created regions of seafloor spreading, and we've also talked about the creation of mountain ranges. The other thing in this region is, because this material, this plate, is coming underneath, it will become liquid, and there is a tendency for this type of material here to punch through the surface and create volcanoes. All right, so how do we know all this stuff? Well, as exemplified by the picture here, if we have an earthquake here, it creates sound waves. And sorry about the noise outside, but if we create sound waves here, and the sound waves are basically being transmitted in two different types: transverse, as well as transverse as well as longitudinal. And they go by a different name here. They go as P waves and S waves. S waves do not go through the core. And the earthquakes, as it says here, are acting like a sonar blip. Okay, so you have a source here, and then at other places along the Earth, we have a bunch of sensors that say, oh, I heard this sound being created, and then everybody gets together and tells each other what were the characteristics of that sound and when did it occur. And by backtracking that information, we can figure out what is the construction, or if you will, what is the structure of the Earth. So this is a picture of how these seismic waves operate, and the difference between P waves and S waves. P waves are ones that are like sound waves that we hear through the air, like you're hearing my voice. And S waves are ones that if you take a slink and you wiggle it back and forth, that's an S wave. Okay, so if you've been in the ocean, you've felt the surface waves, those are S waves. And the P waves are if you heard a sound underneath the water. Okay, so here is an example of a, if you will, this is an earthquake model. I would like it if somebody would make one of these for me.
In New Zealand, because of plate movement, some areas are being squeezed together and other areas are being pulled apart. That means that the Earth's crust, its skin, is either being squashed or it's being stretched. So in quite a lot of places, it's actually broken. And those are called fault lines, and that is what our model is going to show you. You can make it out of very simple things that you can find really easily at home or in a hardware shop, so it's not difficult to make. It's made of these pieces, a piece of wood which has 120 grit sandpaper glued onto the top. So this here is the complete setup for our model. We have two AA batteries with wires coming out. We have a little cheap electric motor which we bought from the hardware store, and we have a thin piece of fishing line here attached from the motor to the spring, which is attached to the eyelet on the block of wood. So this block here is one part of the Earth's crust, and this piece is another part of the Earth's crust. They're sitting on top of each other, but they're not attached because they've been broken. There's a fault there. So the motor over here is applying a constant force, a pull, which is going to stretch our spring out, like that. Okay, so now we're going to give our model a go. Watch carefully, and you can see the spring stretching, and then you will see the block moving, little jumps. And that is what we call an earthquake. The earthquake is when there is movement on a fault line. Now we're going to attach a second block. This could be another part of the same fault, or it might be another fault which is nearby. Often when there's an earthquake, there are aftershocks, little earthquakes which come after the big one that started the whole process off. Hey, did you notice? When the main earthquake happened, it put pressure on this block, and there was another one, a little aftershock. Movements. This spring here is getting more stretched, and away goes our aftershock. So now we've created a model which has three possible different earthquakes. Look how stretched the spring now is. There's a lot of strain on that block. Every time this one moves, it stretches. So I hope you can see how you can make this simple model very easily, and with your friends do all sorts of experiments.
Okay, so here's a more detailed illustration of the seismic wave sonar that we talked about before. So you can see it gets more complicated, but the point is that we have a very good idea of what's going on in the interior of the Earth. We have a pretty good idea of how the Earth is constructed. Now the other thing I want to show you is this whole idea of convection. Now undoubtedly you've seen convection occurring. For example, if you boil up hot dogs in a pot of boiling water, you got to get the hot dogs really warm to get them cooked. And so when you do that, you're going to get a rolling boil, just as we have in the picture here. Now, this particular, not only do I want to show you that, but I also want to show you the diffusion that is occurring, because we talked about diffusion in reference to the core and how diffusion will cause motion as well. So what we're going to see here is from these folks at physics. We're going to see diffusion taking place, and we're going to see a test tube, or it isn't a test tube, but we're going to see a circular type of glassware, as you see going around, and he's going to pour water into this thing, and then he's going to put food coloring, and then in this region here, when they're going to zoom in on the food coloring, I want you to notice how the food coloring is actually moving already. You can see it sort of tenuously moving about. he's going to take this this flame here, and he's going to heat up one side, causing this whole thing to move. Okay, now we're going to notice how the diffusion is taking place. He's heating up one side, and so water is being heated up and rising on this side, and the water over on this side is going to fall. So as we close in, see how quickly it is going? But still, over in the top right-hand corner, you can see that it's actually diffusing out that way as well. Pretty good demonstration of what convection is all about. Okay, thank you guys. Okay, so what causes geological activity? Well, we have, let's see, I think I may have missed something here. Well, I guess not. Okay, so basically we have three different processes going on: convection, conduction, and radiation. When it comes to humans, we have evaporation as part of this system. And so here are some examples showing what would be going on here, you know, and I'll just let them all go as well. So we have...
Okay, here we go.
Oh my, it actually did it.
Sorry.
Okay, here we go.
Now, if you ever decide to do this with conduction, the typical thing to do is just put hot water
Help.
on the metallic surface there, and you can get your tongue off.
Help.
But these are the mechanisms for heat loss for us in our environment. And what we're talking about with the Earth is evaporation isn't part of it. But convection, conduction, and radiation are. Okay, so planetary interiors were or are hot because of a couple of different processes. One is ancient in origin, so the accretion and differentiation when planets were young. Okay, so that sort of differentiation is still occurring, but obviously accretion is really, well, it isn't going at the rate that it was. Although you could, you know, although I think it's something around 300 tons per day of meteorites are striking the Earth, and something like 3 tons of comets are striking the Earth any particular day. But that isn't a lot of energy that is landing on the Earth. And then the other aspect is radioactive decay. So of those two things, 25% is associated with accretion and differentiation, and 75% is due to radioactivity. And part of the radioactivity allows us to understand what is going on in the past. So this is quite involved here. And the most important thing here is that in terms of differentiation, it is true that denser stuff will float to the center, or not float, but sink to the center, and lighter stuff will come to the surface, will float to the surface. But there are materials that love other materials. They connect to them. And so we have we have stuff that's very dense, that's on the surface, and like uranium, like lead, and things like that, and they're sort of in the wrong place, right? But they're not really in the wrong place because they connect to things that are light, like zircon crystals. And so because they're connected to zircon crystals, like quartz and things like that, they float to the surface. All right, so the thing I want to touch on now is that not all planets will cool off at the same time. And so for that reason, we think that some of these smaller guys are actually dead. We'll see when we talk about Mercury that actually we've seen there's some evidence that Mercury's core is not entirely solid, but that's new information, relatively new information. But basically, the moon is quite dead. But the idea here is that smaller things cool off faster. Children, right? You put them in clothes when you go into the snow, they look like little Michelin men, and they're pretty happy that way. And if you see some big guy out there, they're in a t-shirt, and they're pretty happy as well. So you can see it just in looking around at us. And why wouldn't basic physics principles work for us or work for planets just as well as they do for us? Physics is for everybody, not something special.